Our next speaker is Dr. Pedro Rodriguez from the Bionostia Health Research Institute in Spain, and he will be talking about KLF5 upregulation. Is a common event in cholangiocarcinoma acting as an oncogene and constituting a bad prognostic factor.
So good morning, everyone. First of all, I would like to thank Alan and the MMF and the chairs of this conference this year for inviting me to be here today, and MMF for funding this project. So today I will talk a little bit about the role of KLF5 in promoting cholangiocarcinoma. So, as you all know, most of the cholangiocarcinomas are asymptomatic in early stages, which results in a late diagnosis when the disease is already widespread. This, in combination with the high chemo-resistant nature of the tumors, strongly compromise the access of the patients to potentially curative options that are mainly based on surgery, resulting therefore in a bad prognosis, which is mostly below than 12 months in most of the patients. Therefore, it is really important to study the molecular mechanisms that are involved in cholangiocarcinogenesis in order to identify novel common therapeutic targets that could be used to treat most of the patients. So in this sense, we have been studying the Krupel-like factor transcription family. So KLFs are a family of 17 transcription factors that regulate tissue homeostasis and organogenesis, and are also involved in the regulation of tissue metabolism, cell differentiation, and proliferation. Since they participate in the modulation of such important processes, we know that KLFs are involved in carcinogenesis in different types of cancer, since they are involved in the regulation of proliferation, survival, death, and they also regulate migration and metastasis. So what we know that KLFs have been reported in different types of cancer, but the role of KLFs in cholangiocarcinogenesis is totally unknown up to date. So we decided to firstly do a screen and evaluate the expression of all the KLFs in cholangiocarcinoma cell lines compared to normal human cholangiocytes in order to try to identify potential therapeutic targets. And as you can see here, among all the KLF transcription factors in cholangiocarcinoma, we observed that only KLF5 was the one that was only upregulated in all the CCA cell lines tested when compared with normal human cholangiocytes. So what is KLF5? KLF5 is a transcription factor that is highly expressed in the intestinal epithelia, in the colon, and in the stomach, and it has a cell-dependent function, and it depending on the post-translation modifications that KLF5 may suffer, and therefore it regulates cell proliferation, apoptosis, differentiation, and migration. And in the context of cancer, the dysregulation of KLF5 has been related with cholangiocarcinogens in a tissue-dependent manner. For example, KLF5 was regarded to be a tumor suppressor in esophageal squamous cell carcinoma or prostate cancer, while acting as an oncogene in colon cancer, breast cancer, pancreatic cancer, or lung cancer. However, in cholangiocarcinoma, we still don't have a clue on the role of KLF5. So, in this work, we hypothesize that KLF5 may contribute to the development and progression of cholangiocarcinoma and therefore may represent a potential target therapy. So, to do so, we started by analyzing the expression levels of KLF5 in human CCA tumors. Firstly, we wanted to understand which cell types in a human healthy liver express KLF5. By using a dataset of single-cell RNA sequencing from human healthy livers, as you can see here, we observed that KLF5 is mostly expressed, almost exclusively expressed in healthy cholangiocytes, confirming the importance of this transcription factor in cholangiocyte pathobiology. We move forward by evaluating the expression of KLF5 in human CCA tumors from different international cohorts of patients, and we observed that KLF5 was significantly upregulated in human CCA tumors when compared to both surrounding liver and normal bile ducts for different international cohorts of patients. Most importantly, we observed that the upregulation of KLF5 was independent on the mutational background of the tumor, since we observed that KLF5 was upregulated in the tumors harboring IDH mutations, KRAS, or either P53. So we can conclude that the upregulation of KLF5 is a common event during cholangiocarcinogenesis. We also tried to evaluate the potential prognostic role of KLF5 in CCA, and when we stratified the expression of KLF5 according to their expression, we observed that patients harboring a higher KLF5 expression displayed worse overall survival in 3 independent cohorts of patients. Additionally, patients with lymph node affection were the ones showing the highest KLF5 expression when compared with patients without lymph node affection, which further confirmed the prognostic role of KLF5. We confirm now the expression of KLF5 in human CCA cells by increasing the numbers of cells tested compared to normal human cholangiocytes. And as you can see here, we confirm that among all the 9 cells tested, KLF5 was upregulated in all of them compared to normal human cholangiocytes at the mRNA level. We confirm these findings by measuring protein levels of KLF5, and in agreement, the protein levels of KLF5 were significantly upregulated in all the CCA cells tested when compared with normal human cholangiocytes that barely expressed KLF5. Next, we decided to evaluate the role of this transcription factor in cholangiocarcinoma pathogenesis. So to do so, we generated KLF5 deficient cells by using the CRISPR-Cas9 technology. So we first designed the guide RNA guides that we transfected in the cells with these plasmids and selected by selecting the cells that were GFP positive. We confirmed which cells were knockout for KLF5, and we were able to obtain distinct clones, and among them, the levels of KLF5 were distant among them, but when we confirmed by protein, we observed that 2 clones here, clone 2 and clone 20, the one that are total knockout for KLF expression in CCA cells. Therefore, we selected both clones for further functional analysis. So firstly, we evaluate cell growth throughout time, and here you can see that both clones of KLF5 knockout cells display the reduced cell growth throughout time when compared with blister control cells. This was accompanied by a decrease in cell proliferation measured by flow cytometry in both clones, with a concomitant decrease in the expression of proliferation markers PCNA and Ki67. We also measured the cell cycle progression by flow cytometry, and as you can see here, we observed that KLF5 deficient cells displayed a cell cycle arrest at G1 phases that was paralleled by a decreased expression of markers of cell cycle progression, cyclin D1 and SYNDC25A. We also measured colony formation, and we observed that both KLF5 knockout cells displayed a decreased capacity of colony formation when compared with control cells, along with an increased levels of apoptotic cell death measured by flow cytometry. We also measure migration and invasion, and as you can see here, both clones displayed a decreased migratory and invasive capacity that was paralleled by a decreased expression in ECADER1 and PDGFAA. We next decided to evaluate the proteomic profile of these cells in order to try to understand which processes are being modulated by KLF5 genetic ablation, and we measured the proteomic profile by mass spectrometry. So we observed that in clone 2 there were 867 proteins that were significantly altered when compared with control cells, while in clone 20 there were more than 1,000 proteins significantly changed. Among these proteins, more than 400 proteins were common, and when we evaluated the role of these 400 proteins and their potentially implication in oncological process by doing a gene ontology analysis, we observed that the upregulated proteins were involved in important processes such as oncogenic and tumor suppressor pathways, chemoresistance, metabolism, cell cycle, and cell death. On the other hand, the proteins that were downregulated were involved in processes such as migration and invasion and AMT, and also in oncogenic processes. So we moved to in vivo. We decided to inject these cells in immunodeficient mice subcutaneously to evaluate if these cells have a decreased tumorigenic capacity. And surprisingly, we were able to observe that the KLF5 knockout cells did not generate any tumors when we implanted them subcutaneously in the immunodeficient mice. We wanted to confirm this phenotype, and we now conducted an orthotopic model by injecting the cells directly in the liver of the immunodeficient mice. And again, while wild-type cells generated tumors when implanted in the liver of these mice, KLF5 deficient cells did not generate any tumors in the liver of these mice. So our next step was to evaluate how, if we can pharmacological target KLF5, and which would be the therapeutic efficacy of targeting KLF5 with a pharmacological inhibitor. So to do so, we used a potent selective KLF5 inhibitor named ML264, and we incubated CCA cells and normal human cholangiocytes with growing doses of this compound and measured cell viability. And we observed that ML264 induced a dose-dependent decrease in the cell viability of human CCA cell lines while displaying no effect in normal human cholangiocytes. We confirmed this effect by measuring cell proliferation by flow cytometry, and we observed that ML264 was able to decrease cell proliferation in both CCA cell lines. We moved to in vivo, and we injected cells again in immunodeficient mice subcutaneously and treated mice with ML264 for 1 month. And we observed that ML264 significantly reduced tumor growth over time, resulting in a reduced tumor weight at sacrifice. We did the same experiment, but now implanting the cells in the liver, doing an orthotopic model, and as you can see here, mice treated with ML264 displayed a decreased tumor growth, and importantly, while tumor growth during all the experiment was significantly increased in the control mice, in the mice treated with KLF5 inhibitor, tumor growth was not significant, which resulted in a decreased tumor volume at sacrifice. Since one of the processes that we saw that were implicated in KLF5 genetic ablation was chemoresistance, we decided to evaluate what should be the contribution of KLF5 to chemoresistance. So to do so, we came back to our knockout cells, and we treated these cells with the first-line chemotherapy regimen used to treat patients, the combination of gemcitabine and cisplatin. And as you can see here, when we treated cells with gemcitabine and cisplatin, the decreased cell viability was more prominent in the KLF5 knockout cells when compared with control cells. Importantly, when we measured cell death by flow cytometry, we observed that apoptotic cell death was potentiated in KLF5 deficient cells when compared with control ones. We then wanted to evaluate which would be the therapeutic potential of a triple combination of gemcitabine cisplatin with this inhibitor in the growth of CCA tumors. So firstly, we went to in vitro studies, and we treated cells with either GemCs, ML264, or the triple combo containing GemCs and ML264. And as you can see here, we observed that both GemCs and ML264 reduced cell viability, but this effect was more prominent when we combined GemCs and ML264. And what surprised most us was when we measured cell death by flow cytometry, we observed that ML264 alone was not able to induce any cell death, but when we combined ML264 with GemCs, we potentiated cell death induced by GemCs. We then moved forward to in vivo studies. We injected CCA cells in immunodeficient mice, and we treated mice with either GemCs, ML264, or the triple combo. And we observed that while GemCs and ML264 were able to decrease tumor growth over time, when we combined both, we completely arrested tumor growth over time. So finally, we wanted to assess what could be the mechanisms accounting for the KLF5 regulation of CCA chemoresistance. Only a brief overview, there are distinct types of mechanisms of chemoresistance, known as the MOCs, and there are several of them that, for example, could be the reduction of drug uptake or enhanced drug export. We can also modulate proteins involved in survival and apoptosis, modulate of the metabolism of the drugs, enhance DNA repair, alteration in the molecular targets, and also alterations in the tumor microenvironment and EMT. So we came back to our proteomic profile of the CRISPR knockout cells, and we selected some proteins involved in each one of the mechanisms of chemoresistance, and we observed that when we compared the expression of these proteins on the clones compared to controls, we were able to observe several changes in some of the proteins. To get more robust results, we decided to select the proteins that had the same tendency in both of the clones compared to controls. As an example, consider MOC1, which include proteins that are involved in an enhanced drug export. We observed that MVP, which is a protein that exports drugs outside of the cell, were decreased in the knockout cells compared with control cells, which could explain the potentiated cell death in the knockout cells. Similarly, we measured the expression of apoptotic proteins involved in the MOC5A family. Among them, we observed that Diablo protein, FAS receptor, and TNF receptor 10A were significantly increased in knockout cells compared with control cells, which might explain the pro-apoptotic phenotype observed in these cells. On the other hand, when we measured proteins involved in a MOC5B family related with enhanced survival, we observed that proteins such as MET or keratin 13 that are involved in cell survival were decreased in the knockout cells compared with the control cells. Finally, moving to MOC6, we observed that LAMAS5 and LAMAC2 were decreased in the KLF5 knockout cells compared to control cells. So as a conclusion, we observed that KLF5 is increasing cholangiocarcinoma, contributing to cholangiocarcinogenesis by promoting either cell survival and proliferation. And we observed that both genetic and pharmacological inhibition of KLF5 reduces cell proliferation, migration, invasion, and tumor growth in distinct experimental models of cholangiocarcinoma. We also observed that KLF5 contributes to cholangiocarcinoma chemoresistance, and therefore we propose that the inhibition of KLF5 with ML264 may now represent a potential therapeutic strategy for patients with cholangiocarcinoma, and its combination with the first-line chemotherapy may be of therapeutic benefit from these patients. I would like to thank our research group in Biodonostia Health Research Institute in Spain, AMMF for funding, and also our international and national collaborators. And thank you very much for your attention.